Today is December 31st, 2024. This is the Exercise Update Podcast, episode 1, we'll call it. This podcast is going to be a journey. It is going to be what would you call it? A in-progress documentary on the development of these theories, of my theories, of theories that are joined of many great thinkers. This is me trying to understand how to get stronger. Exercise science is quite an interesting field. It was first described to me as engineering principles applied to biological phenomenon. That was when I took it in college, freshman year for the first time. It was ever described to me as a science. I knew about exercise and motivating yourself when I was younger, especially in high school. You got to push yourself, you got to want it. But what I learned over the last 10 years, now that I'm 32, and from college and from study, is that it's biological. You are a biological machine, so to speak, which is also funny because that kind of analogy, and that is an analogy, well, it depends on how you define machine. And we have much more diverse machines nowadays. And what I'm referring to is this idea of thermodynamics. It can be said that we operate like a machine, as nature's most efficient and intelligent machine. But we do not operate on a reductionist level the same way that other machines that we have invented do. Our machinery is still beyond our comprehension. I had a physiology professor tell me something great. He said, physiology is more complicated. The human body is more complicated than all of rocket science. And I can prove it to you. We've built a rocket. And you might say we're close, but remember, we built that rocket first. And we're still working on understanding the human body and everything it can do. That is the goal of science, though, is to understand what is happening in the human body. The goal of science is to understand nature. The original definition of physics meant the study of nature. Excuse me while I get some water. Physics still continues to be the study of nature. We create models in order to help explain nature. But all of science and all of writing and all of the models are a fan fiction of reality. Reality is the only true nonfiction. Everything that we write down as science is a fan fiction of reality. We are doing our best to get as close as we can to the nonfiction. And as we come to understand this world more and more, as we are able to analyze and look deeper and predict and model events that we have never been able to understand or predict before, we must remember that the patchwork of the modeling that we have used is someone's fan fiction of a reality that they understood with the tools available to them of their day. And so we need to use the models and the fan fiction of the past in order to progress. But we also need to do that carefully. And one of the biggest problems with that, the whole reason I'm bringing this up is for calories, because I'm going to prove calories are not a scientific tool in biology. It is bad fan fiction, and we know that it is more fiction than non-fiction at this point with our science, the things that we have been able to prove for the last 100 years. And so I am finishing this copy edit of the book that introduced calories from the father of chemistry, Antoine Lavoisier, in his treatise Elements de Chimie, something like that. Elements of Chemistry in English. It is where the nomenclature, well, I guess this with other supporting documents laid out the nomenclature for chemistry. This one really laid out the nomenclature for chemistry, and this is the official start of the word calorie. And calorimeter. He did write a document earlier about heat in 1783. This document was written in 1789, about 530 pages long. The copy edit I got is about 300 pages long, and that's just because of like a formatting thing. That's actually how long it is about 300 pages in modern text. And so what is the problem with calories, and why is it unscientific and bad fan fiction? So before I went to college, I understood exercise science. Exercise is just, working out, overload, progression, specificity. If you want to lose or gain weight, it comes down to calories in and calories out. That is how I understood it. It was a measurement of energy. And also what I learned in high school in my physics class is that calorie is a measurement of heat. Calorie is a measure to raise 1 gram of water by 1 degree Celsius, or 1 kilogram of water by 1 degree Celsius. At this point, it does not matter. But it generally is to raise a unit of water by 1 degree Celsius. That is a fact of what calories are defined as. And how does that translate into the human body? It's a very interesting question. Because yes, we get hotter when we work out, like our body temperature rises, but we do not operate, we have so much more to our health and nutrition in our bodies than just this measurement of heat. One of the first principles of science is to use like measurements, and you are not the sun, you are not this thermal energy, you are chemical energy. And so using like measure, it didn't make sense to me right away, but you kind of go with it. Energy in, energy out. All right, let's try it. So then it comes down to, okay, where do calories come from? Well, they come from carbs, fats, and protein, and that's the 4-9-4 rule. 4 grams of carbohydrates, 4 kilocalories per gram of carbohydrates, 9 kilocalories per gram of fat, and 4 kilocalories per gram of protein is the equation that we use to get calories. We measure how much calories a food can have by dehydrating it, taking away all of the water, putting it into a box, and using an electric wire to ignite the food. And as the food burns, it's surrounded by water or a temperature, and you can gauge how much heat is being released. How does that make sense for food? Because that's not how our digestion works. it chemically breaks down the food, and the food is absorbed. At no point is the food burned. Because that changes the chemical properties of the food. And I know we break them down, but it doesn't make sense. And so I have looked into the history of this, where it all comes from, and how, because what does seem to correlate, at least enough for it to be useful, is that if you don't eat so many calories, you won't gain as much weight. But doesn't that make sense? Because the calories are specifically tied to grams, so they're specifically tied to a weight. So what if we just took off the heat and we just started measuring things by the weight? So if you measure the weight of the nutrients that you get, the weight of the carbs, the weight of the protein, the weight of the fat, and then measure how much weight that adds to you, that seems to make a lot more sense. And it turns out to actually be the correct answer as well. So measuring things by the grams is going to do more for measuring weight gain and loss, including muscle gain and fat loss. So why are we using this idea of energy and heat? That's an entire philosophy question actually generated at the same time during the 1800s, well, just after this Lavoisier document, because he was the first one to describe calories. And the reason it is to raise water, and the reason it is literally to raise a gram of water, is because Lavoisier had this thought experiment in a time where you knew things could get hotter, but you had no way to measure heat. If what you could notice, because we've already invented thermometers at this point, so you can measure the temperature or the adjacent temperature, however specific you want to get, of a substance. And it's adjacent temperature because technically a thermometer doesn't measure anything but the temperature of itself, and the physics behind it is the 0th law of thermodynamics, that everything is going to come to like an equilibrium. And so we can assume that reflects the general average temperature that is nearest to the thermometer. And so if the thermometer is touching like a hot piece of meat or a cold piece of ice, it will reflect that environment. I know that's a really wordy way to describe it, but some people are very particular about measuring temperature. And so if you have ice has this very unique property where it doesn't heat up like everything else. If you heat up a piece of iron heats up pretty uniformly. Like the surface gets hot and then it gets hotter deeper and deeper. When you heat up ice, the middle stays at 0 degrees Celsius, 32 degrees Fahrenheit, stays frozen, while the outside melts. And so if something is hotter, it's going to melt the outside, but the inside is still going to stay ice cold. And by that, you have a consistent melting for the kind of heat that's being applied. And so if you were just to weigh the water that would be melted from the ice, then you would be able to measure the relative heat that would be coming off from these reactions. And that is a calorie. And that is where calories come from Antoine Lavoisier from 1789. A calorie was an idea of a transfer of heat. Excuse me for the coughing. The heat would be transferred through the, and it's awesome how he even describes it in his book, In Elements of Chemistry. Let's see if I can actually get to the proper quote. It would be in the first chapter. That's about the okay, it talks about how everything has this natural law of attraction, but in heat is this repulsive force that has things separate from each other, and that there is this fluid matter of heat. And this is actually where the conservation of matter comes from. So if you heat up a block of ice, it will expand, according to Lavoisier, 600 times its original size. But if we are to take literally the conservation of energy, or conservation of matter, then that means that the fire is adding matter to the ice in order to make it a vapor and a gas. That is the original thought. So calories are originally literal units of matter from heat. Particles of heat is what calories are. Now we know now with modern physics that there are no particles of heat. There are particles of light, and that kind of stuff can transfer heat. Like, it's a different kind of electromagnetic radiation. And that's something we didn't understand for another 100 years. And he describes it here as well, that hang on. The cause of the heat, or that exquisitely elastic fluid that produces it, by the term caloric. And that's a calorie. This expression fulfills our object in the system which we have adopted, and possesses this further advantage. We are not obliged to suppose this to be a real substance, it being sufficient, as will more clearly appear in the sequel of this work, to be considered as the repulsive cause, whatever that may be, which separates the particles from each other, so that we are still at liberty to investigate the effects in an abstract and mathematical manner. So this is kind of why I started with all that science talk. Let me, again, from his own words, from the man who defined and created the word calories. Besides that this expression fulfills our object in the system which we have adopted, it possesses this further advantage, that it accords with every species of opinion, since, strictly speaking, we are not obliged to suppose this to be a real substance, it being sufficient, as will more clearly appear at the end in the sequel of this work. God, this old English kind of is hard. That it be considered as the repulsive cause, whatever that may be, which separates the particles of matter from each other, so that we are still at liberty to investigate its effects in an abstract and mathematical manner. So, it is this calories, by its invention, is this abstract thought that is understood, that because he talks about it in here as well, that he with our present state of knowledge, we are unable to determine whether light be a modification of caloric, or caloric, on the contrary, be a modification of light. And that's actually an interesting philosophical question, and that'd be interesting to explore, because you have to redefine caloric. Remember that, as we described, it's not real. It's an abstract thought about this repulsive force. And this repulsive force is what we have now coined today as essentially thermodynamics, the energy of a system to move away from the matter, like for the elements of matter to move away from each other. That is the heat of a system. That's the thermodynamics. That's the entropy. Maybe entropy is a little complicated. We'll get into that. This is a journey, but that is the origin of calories. Not even the man who invented it insisted that it was real, that this was like a real measurement. It's just a good abstract thought, a good heuristic model in order to understand heat transfer. This is also where he literally defined specific heat of a substance. This is where all of this physical chemistry starts to get defined. This really is more of a physical chemistry book. It gets adopted into physiology later on, but he also breaks down animal and vegetable substances, like how they're made of carbon. And most vegetables are made of carbon, oxygen, and hydrogen. He was able to determine that. Old charcoal, at this time, he wasn't able to really get down to carbon, or he just called carbon charcoal. He also thought that acid was produced by oxygen, and it wasn't until later on that we reassociated it with the pH scale, which is the amount of hydrogen ions. And it was related to this oxygen because oxygen and hydrogen, as he separated it from water, as he was able to show that water was not a fundamental element. It was made of oxygen, 1 part oxygen and 2 parts hydrogen. He was able to prove that, and show other people how to prove it for themselves. And so that's like what makes this so legendary. And it's just everything is re-verifiable. So he was very, very knowledgeable about all of this stuff, and he was very sophisticated in his application of it. And nowadays we have over applied it because, in all honesty, people have to sell programs, people have to sell competency, people have to sell information like they know it. I really blame colleges and higher education for this, and professional certification companies. I mean, when I went to college in 2015, they taught us the tongue map. They taught us in my nutrition class, they taught us that different regions of the tongue have different taste areas. When I went to anatomy, they said that we've known since the 60s that is not true. And it's just this is an example to exemplify that there has been a giant lack of application of science to nutrition and to exercise science. In the 60s, the most common resume trait, I guess, was for a dean of exercise science was that they were the head of a football program or a sports program. Most of them had degrees in political science. And so when these physiologists try to describe physics, they'd make missteps. And when physicists try to describe physiology, they make missteps as well. Calories was pushed by many physicists, including Michael Faraday, Helmholtz. Claude Bernard was someone who did not believe in this caloric thermodynamics, but Edmund Jules Maury definitely did, and he is very important for many developments in health and medicine. And so people took what these legends said seriously. And today we have the perspective to look back and assess and double check and see where we can do better. So what are we trying to do? We're trying to get the accurate modeling and the accurate measurements, and we shouldn't be measuring things in science that aren't real. So this application of calories is not a real application. It's a thought experiment. It's a thought experiment. It's a heuristic model. And so we can now move beyond that and get into the ground truth models. Which models are true? And so, so what do we study if not this energy dynamics? Like I said before, we study the grams, the weight of the nutrients that we're eating, and the weight that we need. That will help determine the weight of your body and the structure of your body. And the structure of your body is really going to be determined by the signaling. Your body is like a computer AI program that runs nonstop. It is always interpreting the environment around it. And so when you go to the gym, like I need to, you can create a strong enough signal for your biology to adapt. And this is where we start getting into more of like my own personal theory, because now we have to get into the 4 laws of exercise science, the 4 laws of nature that allow exercise science to exist. The first one is that you can get stronger. Biology can get stronger. It can improve its ability to to exist in its environment. That has to get deeper and more intricate. Has to be much more described. But that is essentially the first law, and it is true. You can get stronger. Law number 2. Even identical twins can respond to the same stimuli in different ways. And that just acknowledges that even two people with identical genetic profiles are still not identical people. Each one will be exposed to their own environment. Even a slight change may or may not have a measurable impact, but it has to be known that it is possible for things to change between people. But don't freak out, because law number 3 brings it all back together. We are all defined by the laws of nature. We are all defined by the physics, just like anything else outside of our bodies. And so that gives us our parameters, where we're all still very similar. And remember, we're all similar biologically. Like, some of us can change blood, some of us can change hearts, some of us can change organs, even if we're not related. Never met in our entire lives. But, we all have similar muscles. Like, some people just have may have a tendon different, a connection different or not. But very similar muscle structure. All for most people, at least. There's always differences, whether by birth or genetic or accident or event. But law number 4. Law number 1, we can get stronger. Law number 2, even identical twins, even genetically identical organisms can respond differently to environmental stimuli within a certain degree. Like, there's a degree of variability. 3, we are all bound by the same laws of physics and the same natural phenomenon. 4, we respond specifically. Our bodies adapt to specific signals in the environment. And that is where exercise science comes in, on that third principle especially. So we can identify that specific signals, like, let's say, running versus weightlifting. One's going to get you more muscle mass, and one's going to build more cardiovascular efficiency. Like, we know that by just nature of doing it. Even if you take a bodybuilder and make him start running, he will start building more cardiovascular efficiency. And if he's not lifting anymore, he will lose some muscle mass. And vice versa. If you take a runner and you just have them start lift, they will slowly start to lose their cardiovascular efficiency. Maybe, I'm not saying the rates are going to be equal, but you will start getting muscle mass. And so we have these commonalities. Even if they're a little bit different, and specifically we can just kind of look for what to expect. And so that's like lifting enough weights to grow muscle, or running a drill enough to create the right kind of neural alignment. And then maybe there's just this cognitive factor that also plays a part into it, that makes things a little bit more complicated. But we do know that the body responds to specific environmental stimuli. It responds specifically to specific environmental stimuli. And so by mapping the specific environmental stimuli and how each body adapts to it, and you really just got to do this for yourself or just your small group of people. You don't have to do this for the world. Just a couple people. And then we can understand how we all get stronger. We can engineer our own strength. We can make that true, where exercise science is applying engineering principles to biological phenomena. And so that is the future of exercise science. and it is moving past first this argument about calories. And this podcast is going to start off really hammering in how calories don't exist, or are bad physics, and going through the history of calories. And then after that, we're going to be moving more and more into what is correct. We're going to start with nutrition. We're going to move into should be eating how much of each thing we should be eating, which is, you can write it down right here. Protein 0.545. I kind of like the numbers, how they line up, because everything has a kind of a repeat. 5454545. Anyways, 0.545 repeating grams of protein per pound per day, and up to 0.727. And then outside of that, there's not much more results. You can if you can afford it, but if you're living on a budget, that's kind of where you want to be like, okay, if I'm hitting 0.727, I'm getting as much as I need to get stronger and have maximum development. And then you don't have to spend more money than that. And with the next most important nutrient is going to be your fats, your healthy fats. If you're eating a lot of animal products, you're going to be getting this already. I'm still trying to understand which fats are actually healthy fats. I know trans fats aren't, but it seems like mono unsaturated fats might cause some inflammation, like olive oil. If you're eating it too direct, I think olive oil, there's something about olive oil and vinegar mixed together. I don't know. There's something there. But you still want to make it by the numbers, and initially we're just playing this game by the numbers. We're still learning, we're growing, we're going to get better by it, but playing it by the numbers. 0.454 up to 0.6 grams of fats per day. You want to average probably closer to 0.545. But if you want to get up to 0.6, that's totally fine, because those healthy fats are really good for your body. Yeah, and most animal products are going to be pretty close to that. I got to do more investigation into all this and try to really understand it, but that's all next. I got to get through the history of, got to explain why calories are dog water, and move on from there. And we already know protein is good, getting complete proteins. We know we're going to need some healthy fats. We just got to kind of understand that a little bit more. Nucleotides, we got to understand. You got to breathe good. You need good oxygen getting into your lungs. Water, of course. You need a good source of light, at least a little bit. It is a nutrient. It's a material nutrient. You got your fat-soluble vitamins, your water-soluble vitamins, your major minerals, and your micro minerals. And that's your 11 nutrients that you need to get to your body from nature. Carbohydrates, if I didn't mention them before, is just a multiplier from protein. If you're going for weight loss, you're going to reduce the amount of carbohydrates 0 to 2 times the amount of carbs. You can go total ketogenic or just a little bit of carbs. And if you're going for performance, then it's times 3 to times 4. And even if you're doing weight loss, you could kind of edge yourself closer to the times 3 times 4, depending on your source of carbohydrates and how much you're actually working out. But because if it's like mostly vegetables, you're going to have a hard time getting up that high. So you could try, and you don't have to limit yourself at all. If it's mostly, and I don't mean mostly by volume, I mean mostly by weight of nutrients. Because a cookie has a lot more weight of carbohydrates than a banana does. Maybe, but more than cauliflower does. The weight of cauliflower versus the weight of the nutrients in cauliflower it's a very lightly dense food. And so you could kind of think about foods like that, like nutrient density, like how much is in there of what, and like nutrient density and proportion. Yeah, so that's kind of a lot of information to start for podcast number 1, but that's the idea. We can understand our health a lot more from here, and I will try to continue and advance on from this. I got to go back and finish this book, but I did want to get at least something done with this kind of like piece. So yeah, calories, don't use them anymore. How do you lose weight when you're working out? Remember that you want to activate as many cells as possible, I guess is the simplest way to think about it, because you would need to use those nutrients. You can only cut into the weight of the nutrients by using those nutrients. And so we activate as many cells as possible to just not in like in an obscene way, but just to grow, to get stronger. You have in your bicep alone, in just your main bicep muscle, your bicep brachialis, you have 500,000 muscle fibers. 500,000 fibers. In your calves, you have 1,000,000 in one of the muscles. And that's just, I think that's just in your gastrocnemius. You got another soleus muscle back there too. It's 1,000,000 muscle fibers. So that way you can have all this dexterous control. Your cerebellum in the back of your head has over 50% of the neurons. So that way you could be one of the most dexterous and physical animals ever to exist. And so take advantage of that. And that is how you lose weight, is by activating as much motor units as you can. Refreshing and gaining more dexterity, strength and range of motion, strength and action, strength, like range of strength, like being strong not just here, but also over here. And then being able to move and stretch the way that your joints should be. Some people have injuries like myself. Some people have calcified joints, arthritis, and all I can say is these are all cells, and there's a way to strengthen them or to align them, and it may be painful sometimes. It shouldn't be painful all the time, and in the long run it should be less painful. I was able to get there. Hopefully you can too. I'm not saying pain-free. I'm just saying less painful, more manageable. You become stronger. And so you are able to walk with the weight. And sometimes, it's just as annoying as ever, but you become stronger. And so you're trying to lose weight. Learn new skills, take boxing, take kickboxing, learn a sport to try to become good at a sport, practice like an athlete for that sport. And in learning those skills, you're going to be activating so much new cells. That's why athletes have the best bodies, because they have so much cellular activation. And so if you want a body like an athlete, you got to increase your cellular activation. And this is and as you increase it, your cellular activation will become easier and stronger to activate those cells again and again and again, as your body takes those weight of those nutrients and reconstructs them into positive structural changes. And so that's where we're going, man. And this is the genesis of that, which is crazy. So many other people have done so much good work in exercise science and nutrition. So this is not me carrying the weight. So many other people are carrying so much weight. I am simply trying to cut through the veil and show the world what exercise science is, and no longer let people misconstrue or sell something less than what is this miracle. And so, yeah, it's about cellular activation, and it's about the weight of the nutrients. the amount of the nutrients, the mass of the nutrients, however you want to describe it yourself, the grams of the nutrients, the micrograms of the nutrients. That weight of the nutrients is going to change the weight of your body and how those weights shift, like bone weight versus fat weight. It's all based, some nutrients are going to be the same, but some are, we got to get specific and tell it, like, hey, we're doing this. I don't know. I think that's probably a bad example because I can't think of a nutrient reason why the bones will get strong. If you had a lack of nutrients, though, it would make it difficult. Lack of vitamin D, lack of calcium, so that's why we got to make sure we get enough of those nutrients to make sure that our cells still work. So this argument still works. But like bone strength is going to come from, it's Wolff's law. It's the bone will remodel itself based on its environment. So you lift heavy weights, you get strong bones. Very straightforward. And it's those principles that most of our cells seem to operate on, where if you are able to stress them in the right way, then they get stronger. The same way that I guess us as the metastructure of cells can rise to a challenge and get stronger. It's pretty interesting. There's different avenues to go, because we can go philosophical, we can go back to the science and back to the weight loss. We can keep going in different ways, and that's kind of what I like about this. And we're gonna go in a bunch of different ways. We're gonna try and touch everything in this giant map. We're gonna explore the whole world of this new concept of exercise science. And first, we have to dethrone the former king, calories. It is not a proper use of thermodynamics. It's not a proper use of physics. It is not a proper use of nutritional or exercise science measurements. And we never need them again. Measure your nutrition in the weight of the nutrients. Measure your weight loss or weight gain by the signal you tell your cells to do. Wait, if you want to burn more fat and lose and look and develop muscle at the same time, activate more cells. Like an athlete, activate more cells, learn more skills. The best athletes look the best. The best athletes are constantly improving themselves. They're learning new skills. They're getting a little bit faster. They're getting a little bit stronger. How? They're improving their cellular activation. And you can do the same because you are biology just like them. We're all human and we're all capable of great strength. Now I'm really motivated to go to the gym. I got to go to the gym now. But, that being said, that is what I said. Yeah, completely move away from calories. Again, I'll be going over more of the history of calories. Probably in the next episode, I'll be going over Lavoisier's history of the calories in depth. I think that'll be good. Because then I'll be done with the book by then. And then it's like, that's a good summary of everything that he talks about and getting that information together. And then we'll start to rapid fire. Well, I got to do the preface too of Lavoisier, so maybe we'll do 2 episodes of Lavoisier. One is going to be dedicated to calories, and one is going to be dedicated to Lavoisier himself and like his genius way of thinking about the world. A very capable mind. And so then from there we will move into the history of the 1800s and how the physiological reductionism came into play. And then we will move into the 1900s when we actually started to understand the materials of nutrition. And it is also the birth with Dudley Allen Sargent of modern exercise science. So that'll be fun. But first, gotta get through the 1800s, through the philosophy, through the social changes, through the business and labor power, and the concept of thermodynamics. We got to get through all that. First, calories, next episode, then Lavoisier, then the 1800s and energy, and that might be its own couple series. The 1900s and real nutrition, and then we'll eventually get into the modern day and what is good nutrition and modern recipes and cooking techniques and becoming a modern day nutritionist. And then that'll cover everything in nutrition. We'll be done with nutrition for at least the general aspect, because we could branch more into it if we want. But then we'll move from there to exercise science, exploring the 4 laws of exercise science, the biology, the physiology of human adaptation and development, and we'll change the world just one step at a time. Thank you for listening. If you want more content like this, like follow, subscribe. You could definitely find me on YouTube. I don't know where else you can find me right now, but find me on YouTube. Maybe if this podcast is on Spotify, then that means I figured that out, and you can keep finding me here every time I'll post an episode. Thanks for your time. All right.